Hey kiddos, happy week 7. This video is for our synchronous class. If you were in class on Thursday, October 15th, then you already got this lesson and you can skip to the last video in which I'll give examples of different types of problems that we can solve using our equations of motion. All right, so in our lesson today, we had goals of being able to access our ability, I assessed your ability to describe motion graphically. If you haven't yet taken the Graphing Motion Check for Understanding quiz on formative, please see me so that you can do so. And then I also will work on deriving some equations of motion, and we'll show you how to use those equations to solve some problems. All right, so the quiz on Go Formative was very similar in style to problem number 70. So a runner at position 0 at time 0. The finish line is 100 meters away, and every 10 seconds the runner runs half the remaining distance to the finish line, running at a constant velocity in each section. Draw a distance or position versus time graph and a velocity versus time graph for the first 40 seconds. All right, so when we're graphing motion, time is always going to be on the x-axis, just in the units that they're given in the problem, and position or distance will be on the y-axis in the units that are given in the problem, so position in meters. And we're starting at 0, 0. And it says the finish line is 100 meters away. So we'll kind of mark that 100 meters as our maximum position on our y-axis. And it says to draw our graphs for the first 40 seconds. So that will be the maximum time on our x-axis. All right, and then we can sketch in some intermediate times. Making an effort to kind of approximately space them appropriate, right? Even spacing for each 10 seconds. All right, and then we've got our just a little bit of scaling for the y-axis. Okay, so we're going to start at position 0, time 0, and every 10 seconds, the runner runs half the remaining distance to the finish line at a constant velocity. So the first 10 seconds, we're starting at 0. Half the distance to the finish line is 50 meters. So at 10 seconds, the person has run 50 meters. And we're assuming a constant velocity in between them. So it'll be a straight line. Okay, the next 10 seconds, we'll cover half the distance again. So halfway in between 50 and 100 is 75 meters. So at 20 seconds, we're now at position of 75 meters and draw a straight line. And then the next 10 seconds, half again. So it's like 87.5 meters. Let's see here, like so-ish. Okay, and then we can do it again. Okay. And so we're kind of reaching an asymptote here. So this isn't perfect, but it gives a big idea at what time we're at what position. Now, this is a garbage way to run a race, right? There's no way you'll ever win the race if you're not going at least a constant speed, if not speeding up during a 100-meter dash sort of race. And this is the difference between physics and math. A mathematician would look at this and say, that runner will never finish the race. But in physics, we'll beg to differ, right? If you're covering half the distance every time, eventually you'll get close enough where you can just go ahead and reach your arm over the finish line. Okay, so we use math as a tool to represent something physically that's happening. Our limitations are based on our size, shape, speed, not based on like an idealized mathematical argument. Okay, so this is our position versus time graph. Now let's turn that into a velocity versus time graph. Okay, so I'm going to draw a velocity versus time graph directly below my position versus time graph. I like that because the two graphs can be directly comparable if they're on one right below the other and on the exact same time scale. Okay, that's very convenient. So, right, 10, 20, 30, 40, right, time in seconds, and then velocity in meters per second. Okay, so you'll notice that I've got my x-axis running through the middle of my y-axis, so I have access to positive and negative velocities. Okay, I think that's good practice generally. So now let's go ahead and graph these. All right, so to find the velocity is always the slope of a line on a position versus time graph. So if I go up to the first 10 seconds, I want to find the velocity. I've got 50 meters in 10 seconds. So the slope is 50 over 10, which is 5 meters per second. All right, we know that is the fastest this person will go because that's where they're covering the most distance in a 10-second time frame. And also we see that line has the steepest slope on the graph. Okay, so that means 5 meters per second will be my maximum value on my velocity versus time graph. Okay, and this person has a straight line that says the problem actually says we're moving at a constant velocity in each segment, right? Which means the velocity versus time graph will be flat. Okay, a constant 5 meters per second for those first 10 seconds. Right, and then the next one, we're going from 50 to 75, so a rise of 25 and a run of 10. Okay, so that will make the velocity 2.5 meters per second. And we can draw a line right here. You really didn't even need to calculate that because we know half the distance is being covered in the same amount of time. So you know it's half the velocity, and so you can just eyeball it. And that's what I'm going to do for the rest of them. Half the velocity for the next segment. Right, and then half the velocity for the next segment. Now, I've got a question for you. What would happen if at this point, instead of going forward, right, a little bit slower, what if they're like, oh, I dropped my phone back at the 75 meter mark? Okay. Would that line go up? Would it go backwards? No, if they had to turn around and go back to the 75 meter mark, that line would go back down towards the 0 position mark. It'd go backwards, a negative slope. Okay, and this negative slope would result in a negative velocity. Okay, so for that blue line on the position versus time graph, you would draw a negative velocity indicating it was going a different direction. Negative slopes equal negative velocities. And then finally, don't connect these with a vertical line. You can indicate that these bits of motion are connected by just drawing dots between them, or even leaving them blank is fine. All right. Cool. So let's look at deriving equations for motion. So we only have one equation for motion so far that we got from the graph of my daughter walking down the sidewalk at a constant speed. So this is for constant, oh, can't spell. Constant velocity motion, d is equal to vt. Okay, and I'm going to give you a bit of information about resources that you'll have in my class. Now, in IB Sciences and I think in IB Math classes, you're given an IB data booklet, which has all of the equations and resources that you'll be allowed on the IB exam. In the first year of the course, that's a pretty fat equation sheet. And we won't use all of them this year, and not every student is going to actually continue to the second year of the course. And so I'm not going to print those for everyone, but I do encourage you to not only take notes, but after you're done taking notes, go back and pull out the important equations and start building an equation sheet for yourself. This should be something that you start now and that you add to as we build more tools, add more tools to our toolbox for problem solving. So in your equation sheet, you'll have motion equations, you'll have equations for force, for energy, for momentum, okay? And so you'll have a master equation list at the end of this school year. Okay, so let's go ahead and derive some equations for motion. I'm going to do a position versus time graph and a velocity versus time graph. Okay, so if we've got something speeding up down a ramp, right? You can imagine a car rolling down the ramp and it will be picking up speed. Let's draw position and velocity versus time graphs. The velocity versus time graph is easy, right? If we're assuming we're starting from rest, if something's speeding up at a constant rate, the velocity is steadily increasing. So this is assuming that the initial velocity is 0. If an object at time 0, if we start observing the motion of an object continually speeding up, maybe it has an initial velocity, it would have a y-intercept. So the initial velocity does not equal 0. They would have the same slope if they're accelerating at the same rate, but the other one would have some initial velocity. Okay, so this is a linear equation. So we would have the velocity at any point in time equals some slope times time, which is on the x-axis, plus the y-intercept, v initial. Okay, what is the slope? Well, the slope is the rise over the run, right? The rise is the y, is the change in velocity over time. And that's actually what the slope is, the change. It's not really just the change in speed, it's the change in velocity. So I'm going to put the little vector marker there over time. And that's actually defined as acceleration. What units are acceleration in? Well, velocity is in meters per second. Time is in seconds, right? So the number of meters per second that an object is speeding up or slowing down for every second it's moving, this is oftentimes abbreviated as meters per second squared. Okay, so it's acceleration. The slope, whoopsies, is acceleration. Okay, sometimes this is written as v equals at times v initial. What we're solving for is how fast an object is going if it's accelerating at a constant rate for a set amount of time.